And welcome back to experiment 11 of my Electronic Experimenters Kit series of videos, the common emitter with emitter follower. Just before I start the video, a quick shout out for this channel's sponsor, PCBWay, your one-stop shop for all your PCB requirements, be it prototypes, assembly, flexi rigids, CNC machining, 3D printing. The instant quote is easy to use. Just put in the dimensions of your board, number of pieces, how many layers, thickness, etc. Upload your Gerbers, hit the quote now button, and you're good to go. And delivery is very fast. PCBWay supplied the boards for the electronics kit. So, back to the video. Here we have the common emitter amplifier based on the circuit at the end of experiment 9 part 2, and we have the emitter follower. Now the idea of this circuit is to give you the best of both worlds, the input impedance of a common emitter and the output impedance of the emitter follower or common collector. So we're going to use the same sort of ideas again to work this circuit out. Basically we want about a volt on the emitter, and we also want to have about 2 milliamps flowing down through the emitter. So there we go, there's our kind of very first starting conditions. Whether we're going to get exactly 2 milliamps or, you know, there's tolerances everywhere. Gains and tolerances all make a play. So 1 volt 2 milliamps is 500 ohms, and I've got this split so that we've got 390 ohms that can be bypassed by the capacitor, so they're taken out of the AC gain equation but not the DC equation, and 100 ohms here, so that we kind of swamp the intrinsic emitter resistance, so we don't get affected so much by temperature. So again, you know, we've now got 490 instead of 500, and so 490 times 2 milliamps is 0.098 of a volt, so we're slightly under, but we won't worry about it at the moment because, like I say, tolerances will make that different anyway. So then we can bring in the base voltage, 1.6 volts, about 0.6 volts higher. It could be anywhere between about 0.5 and 0.8. You know, it all depends on the transistor. But I normally take 0.6 of a volt as somewhere as a starting point. So that sets that up. Of course, we can then, you know, ignoring the base current, we can then set up a divider from 9 volts to give us the 1.6 volts. So we now know we have about 2 milliamps flowing down there. So what is the voltage at this point? Well, it's 2K2 times 2 milliamps, which is 4.4 volts across it. We divide that from 9.9 volts, and that gives us a voltage here of 4.6. Now we know that the voltage here will be 4.6, and the volt drop across here will be 0.6. So we should be expecting to see 4 volts at this point. Now I've given it a reasonably low emitter resistor because we want a reasonably low output impedance here. So I picked 470 ohms, which means that we'll have a current approximately 8.5 milliamps flowing down here. And based on the circuit from before on 9.2, the gain here is 2K2 divided by 100. So we are expecting to see a gain in around of about 22. So let's go on and look at the board itself and see how close we are to these figures and how close we are to the gain. Right, I've started building it up so you didn't have to see that. Did it off camera, and so we'll bring in the meter so we can look at some of the voltages. We'll just connect that to the ground, and I've got a DuPont lead so I can just plug in. We'll start off with looking at the emitter voltage. Oh, better put some power on first. Power coming up now. So you can see this is where we're looking. We should have 2 milliamps flowing down here and 1 volt, but we haven't. We've only got 8.47. So we've got less than 2 milliamps flowing down here. Not an issue, it's just tolerances and things like that. That's the voltage we're getting, 0.84 or 0.85, and we were hoping for 1, but tolerances and things in the different transistors. It's as long as it's in the right ballpark. So we're going for 1.6, but we've only got 1.5. So, you know, nothing to cry about. It's all in a safe area. Look at the collector. So we're now looking here. So we're expecting 4.6 there. We're getting 5. So instead of being 4 volts here, we'll expect to be a bit higher. So I'd expect to see about 4.5, something like that. So we'll move over to there. And 4.47, so about 0.6 of a volt across there. We could always just confirm that by moving that to there. And there we have it, 0.68 of a volt. So that's the DC conditions, and so relatively close to what we were aiming at. So let's put on some AC and have a quick look at that. I'll just move the meter up, just remove the meter for a bit. Right, I've brought the scope lead in, channel 1, channel 2, and the oscillators coming in on the cable here, grounded to this point. So we'll pop up the scope on the screen. Yellow is the input, blue is the output, and so you can see we've got a smaller trace on the input. One's at 5 millivolts per division, and the output's on 50 millivolts per division, so we have gain there. So if I take my trusty DVM again on AC range, pop it on there, pop it on that one, see what we get. It's going to be pretty crude because we're going to be down a bit low down here. Well, actually, if we up it a little bit, shall we? We should be able to go up to something like 10 millivolts. There you go, it's like around 10 millivolts. Let's change the range on the scope. Again, you can see we got 20 millivolts per division on the input and 200 millivolts on the output. So let's go and see what value we got on the input, on the output, sorry, 10 millivolts going in, and we have, get it to go in the hole. $154. Oh no, it's gone up again. 200. Oh no, it's wobbling around. Maybe I haven't got a very good connection there. Let's move that out the way. Push it in there. So that reckons about 211. So 211 divided by 10. You could do that in your brain, couldn't you? 21.1, and I think we calculated the gain out to be 22. 220 divided by 100 ohms, so 22. So we are close to what it should be, which isn't bad. Just to show you where the gain is coming from, because in this circuit there's two parts, as you can see on the up there. There's the common emitter, which is this section, and then there's the emitter follower, which is this section. And as we got from our previous experiments, we have voltage gain in the common emitter, but we do not have any voltage gain. We have less than unity, so we actually lose voltage or lose gain in the emitter follower. But what we do benefit from is this has a high output impedance, this has a high input impedance, but a low output impedance. So we're gaining sort of like some sort of like power gain. That's giving us the voltage gain, this is giving us some current gain. And the inversion is happening in the common emitter. So if I move this over to here, we have, if I move that as well, we should have probably a little bit more output there. Yeah, a fraction. 211 was it, and now it's 212. We have gain there, and as you notice, up on the screen, there is 180 degree phase inversion. Now if we move the input, I'll just move the meter out of the way, and we move the input to there, that's going to go clonkers. And we move the output back, the output signal scope back to there. Right, so now you can see that on the scope up there that the phase is the same, and if I bring it down, according to the scope, the gain is the same, but it isn't. It's slightly less than 1. It cannot be, it's less than unity, so it's just within the accuracy of the scope. And here's just a quick overview of the common emitter and the emitter follower and the impedances you could expect to find and the voltage gain. So that's a little bit more information on the two ways the transistors were used in this experiment. If you want to see more like this, hit subscribe, hit the like, hit the notification bell to remind you when the next one comes along, and I'll catch you on the next one.